neglect air resistance, I get up there, right? All right, but rather than getting up at this point, I'm going to get at this point a different way. I'm going to get up to that point by walking up a hill. Now, if I walk up the hill, and it's going to be a sandy hill. You ever try to walk up a sand dune? Not supposed to, because there's stuff growing and all that stuff. They say, don't walk on the sand dunes, you'll get like an $800 fine or something at the beach. Well, there's places you can walk up sand dunes. You can see the Mojave Desert or something, the Sahara Desert. You see the people walking in sand dunes and everything. What was it? The Aquaman movie, they were walking in sand dunes in the Mojave Desert. Well, if you had to walk up that sand dune, is there a lot of friction you got to overcome? You got the sand moving and all that friction. Gosh, when you get to the top, you're worn spank out. Now, the energy change to get from here to here, you just had to go against gravity. Jump, go against gravity. Here, using this system involving friction, then the energy it took to get there was a whole lot more. And being conservative, if you just jump back down, you're so tired you just lay down. You just fall down. And if you do that, your energy change is just the energy due to gravity that you would get here as he falls back down to the ground. You don't get any energy back from the friction. That's gone. That energy left the system. Nowhere to be found. All right? It's like change in your pocket when you wash them in the washing machine. It's gone. You never find that stuff again, right? It's like socks. You ever notice socks just disappear? I swear there's a separate universe, the sock universe. They just suck wormholes and they just go away. You never see them again. Socks rule the world. And, who knows? But that energy is gone. You cannot get it back. Friction is a non-conservative force whose energy leaves systems and cannot be transferred back into something else. It cannot be transferred back into something else. With here, we got, kinetic energy going up to potential energy and back to kinetic energy. Air resistance is friction. It's air friction. So let's think about it. Say I can jump. Say I'm a flea. A flea is a good example. I could be the lead guitarist for the Red Hot Chili Peppers. Flea, right? Give it away now. All right. So I'm gonna be flea. And since I'm flea, I can jump really, really high, right? Like 100 times my body height or something. So I jump up to 100 times my body height. To do that, I'm at the really fast velocity. 100 meters a second, let's say. Who knows? I'm making stuff up, right? So I jump up 100 meters a second, some initial velocity. And I get up here. And as I fall down, with no air resistance, my final velocity would equal my initial velocity. That's a conservative system, no air resistance. I throw air friction in here, air resistance, and as I fall down, do I reach the same velocity? It's not equal to each other if we include air resistance. It's not equal to each other if we include air resistance. Here, if we include air resistance, V final equals the terminal velocity. I'm at the edge of the screen, I think. Equals the terminal velocity that we talked about earlier if we include air resistance. So the velocity hits the ground is not going to be the same as he jumped up. Another good example is if you take a rifle, shoot it straight up in the air. But when it leaves, it's going to leave with the muzzle velocity, right? And for 22, let's say 1,500 feet per second. That's pretty fast, 1,500 feet per second. That's about 3.5 seconds for a mile. So 1,500 feet per second going up. I'm going to shoot it straight up. Now I'm going to be smart. I'm going to do this. So it lands right there and hit me on the head, kill me, right? But the problem is it the same as turning that rifle upside down and shooting me on the top of the head? In reality, no. Because there's air resistance. There's a terminal velocity. If I did it on the moon, assuming it wouldn't be escape velocity on the moon. Say I did that on the moon, it basically has no air resistance. So there's basically no air friction, we can say. If I did that, might as well turn it upside down and fire it back down, because you know what? The velocity it would hit me on the head with is the same I left it with. But that's the moon. That's a conservative system. There's basically no air resistance. Here we have a fluid we're shooting that through that causes a terminal velocity. So as I shoot it straight up, as it comes back down, it's going to be traveling at the terminal velocity of that bullet, which I have to do the calculation on what that is. And actually, that equation for a bullet, something about the size of a 22 round, it's going to be a slightly different calculation of what you would do with bigger objects when we did our equation for terminal velocity. Okay? Conservative systems, forces, a conservative system, basically, energy doesn't depend on how you get there. Path doesn't matter. Energy stays in the system. Non-conservative forces, their energies leave systems and you can't get it back. So the conservation of energy works. Nothing leaves the system if there's no non-conservative forces. If there are non-conservative forces, energy will bleed out of that system. Okay? Hopefully it makes the point. The book goes the traditional mathematical route. I've taught that before. It made a lot of glazed over eyes, and I will, if you have me for 301 classical mechanics, I'll discuss it there from more of a mathematical point of view. All right? At the very last, they talk about the energy principle revisited, and basically there they just include all the energy of all the system, all the energy that the system could deal with. So let's look at that real quickly. They've got some examples, and they can get hard because the key here is to identify what's potential energy, what's kinetic energy, and what are the other energy systems, spring energy, thermal energy, friction, that sort of stuff. What is the work done? So for 10.8, the energy principle revisited. For some of you, revisiting a principle probably wasn't a good thing in life, right? In school. I tried to avoid revisiting principles myself. That's an AL, not EL. And what it's basically saying just is, again, as before, that the energy in equals the energy out. But let's include all of them now. So, if we include all of them, and make sure I say this right. That the kinetic energy in plus the potential energy into a system plus any thermal energy, some thermal energy, it's going to equal the kinetic energy out plus the potential energy that you have out after an event occurred, plus the thermal energy you have after an event occurred. Rather than energy out, energy in, let me change this to energy before and energy after. That's a little bit better way of doing it. My apologies there. We'll do IN is initial, or IN stands for initial, and out we're going to use final. I'm sorry for doing this on the fly, but this is a better way of doing it. Thermal energy, final, plus the work done external, some external work. Now, that could be work that the system did and left the system. That could be work that was done to the system. I raise something up. I do work to the system. So this can be positive or negative. Be positive or negative. So you take the initial kinetic energy plus the initial potential energy plus the initial thermal energy, and that's going to equal the final kinetic energy plus the final potential energy plus any the final thermal energy of it. Then you take into account any work done to the system. If work was done to the system, at the end you add it because it's got more energy than it had before. If the system does work, you put a minus there. I'm going to write this down. So if work done to the system, add work. If the system does work, here, as I lower it, this actually did work to be lower because it's now got less energy as it had. If work system does work, subtract the work. Okay? You subtract the work. Think of also, subtracting work is a good idea if you think of it just as people as a system. As I run around and do things, I'm doing work. So that my potential that I have inside got decreased. So I have to subtract all that work I did to find out my new potential I had. With bar charts, with budgets, with dollars. If I've got $100 and I have to do something that costs me $10, I give somebody $10, now I got 90 left, right? Well, that $10 left my system because I wanted something done. Hey kid, mow my yard. If I can get it for $10, that's really good. So I'm paying him $10, right? Mow my yard. The kid mows the yard. I'm an old grandpa now, so I only got like a quarter acre. So $10 would be right? Give you 20. I'll give you 20 total if you do the weed eating too. So he get 20. That's good. So the kid's gonna mow it and weed eat. So he didn't work for it. So work was done by the system. The kid did the work, but to me, to get that done, what I have to do, money's got to leave my system. So the system does work, I've got to subtract it out. Because now I've got 80. I had 100, got 80. My potential is a lot less. My money potential is a lot less because I had to pay that kid $20 to get work done. Okay? Hopefully that made a little sense. And they do an example in your book. The one they have in the book, the challenge problem, it's kind of complicated. They made it overcomplicated, but the whole concept of pushing something in and then having it, or pulling on it, doing work pulling or pushing on the spring, that's actually a good type problem. That's something I would put on the test. I would make it a little bit more clear and lucid for you how to solve that type of problem. So how do you solve them? You just look at it and go, does it have any kinetic energy? It's not moving? 0. Does it have any initial potential energy? If the spring was compressed, the test, maybe that's spring energy, 1/2 kx squared. If the spring's not compressed in the end, it's got no spring potential energy. If the spring, springs, like that word springs, sprongs, S-P-R-O-G-N. Yeah, we let it go. That's kind of an alliteration because it's just how it sounds. No, that's not alliteration. It's something else. So it would have no potential energy which we release the spring. That's a much better way of saying it. And you just go through and evaluate each one. If we don't talk about any thermal energy, it's just zero. We don't assume any change in it. And you see what the problems got. There'll probably be work done in these problems, so you got to take that into account. And there'll be some change in potential and final, and probably some change in, it may or may not be in initials. There'll be some potential initial or kinetic initial. You just have to kind of look at the problems and see. Here you just work the problems. You just work the problems. And I gave some good examples. I'll try to work on Friday real quickly at the beginning of class. And then we're going to go into momentum and impulse, which I like the concept of momentum and impulse. It's got some limitations to it, so you got to understand where it works and where it doesn't, but the concept definitely works. And actually, Newton described his second law in terms of momentum. Actually, he didn't say F equals ma. F equals ma. Isaac Newton. No, he didn't do that. He actually said that force is the rate of change in momentum. That's the way Newton, in his book Principia, described it. Okay? So that's the end of chapter 10. Hope you had a good time. Enjoyed the lecture. Have fun writing your notes on it. And see you guys Friday.